When we use the Forward Euler method to simulate classical mechanics, we see that the systems pick up energy, artificially pick up energy. For instance, if this is the Earth and this is a satellite, and we compute the motion of that satellite around the Earth, we are not finding a perfect ellipse, but we are finding a trajectory that grows and grows. The energy of that satellite increases. This is a general phenomenon with the Forward Euler method in classical mechanics. And in this video I want to show how to compute the rate of growth of energy, of artificial growth of energy, I should be saying. Be aware that this comprises lots of algebraic manipulations, but no integrals whatsoever. We'll start by writing down the equations for one single step of the Forward Euler method. So, the position after the step is the position before the step plus the step size times the velocity before the step. This is how Forward Euler computes the next position. We increment our current position by the time that step takes times the velocity at the beginning of that step, which isn't perfect because, of course, during that step the velocity is going to change. It's the approximation that's core to the Forward Euler method. Similarly for the velocity after that step is the velocity before that step plus that step size times the acceleration. Newton says force equals mass times acceleration. So the acceleration is the force divided by the mass. For simplicity, I'm working with a force that depends on position only. So F of x1, again the force at the start of the step. And I'm doing all of that in 1D, which makes things easier. You can do that in 10,000 dimensions, but then it's pretty hard to write this down. You need to think about vectors and matrices and things like that. I don't want to delve into that. So this is one single step of the Forward Euler method. What I'm interested in now is the change of energy. Let me write it like that. The energy after the step minus the energy before that step. What would that be, the change in energy? First of all, it's the change in kinetic energy. So 1 over 2 the mass times the velocity after the step squared. That's the kinetic energy after the step minus the kinetic energy before the step plus the change in potential energy. I'm assuming that this force derives from a potential, which I denote by V, capital V. Be careful, lowercase v for velocity, capital V for potential. So that's the potential energy at the position after the step minus the potential energy at the position before the step. And what I want to compute is some average size of this energy difference. Obviously, this energy difference tends to be positive, so that we get an upward drift. First, let's look into kinetic energy. You spell this out, which yields 1 over 2 mass v1 squared plus 2 times the velocity at the start times step size force over mass plus step size force over mass squared minus the initial kinetic energy. 1/2 mass times initial velocity squared, and this one cancel. Nice. So what remains is 1/2 times 2 cancels initial velocity times time step times force at the start over m plus step size squared, force squared, mass, it's just one mass down here, and we have to include the 2. This is the difference in kinetic energy. The ugly part is this one, the difference in potential energy. So the potential at the position after we did the step, what could that be? We know what that position is. It's the initial position plus step size times initial velocity. So what we're interested in is the potential energy, that is, at initial position plus step size times initial velocity. We need some handy expression for that. And the trick to be using here is the so-called Taylor expansion. Let's say this is the exact potential, as it depends on position. So for this position, I've got this potential energy. For this position, I've got that potential energy. I'm sitting in a valley here, so this would be a stable position, and so on. Let's say this is x1, my initial position, and I'm interested in that potential, capital V, at this position, x2. The distance between those two positions would be step size times initial velocity. And now I try to figure out some approximation for that potential at x2. First of all, this is more or less similar to the potential we had at x1. So this would be the potential of x1. But obviously, this is not it. We have to have some correction. The next correction that we can introduce is the following. We form the tangent to that V curve at x1. So this would be the tangent. And now I'm using this triangle here, this triangle, to come up with a linear approximation. If there was no curvature to this function V, if it was a line, then this value would be the correct one, the exact one. I can compute the length of this leg of this right triangle because I know the slope of this line. The slope of this line, the slope of the tangent, is the derivative of our function. That's the role of the derivative. It tells you the slope of the tangent. So when I know the slope of the tangent and when I know how far I go to the right side, h times v, I can compute how far I go up. The derivative tells you the ratio of this leg to this leg. So now we've got two terms as part of an approximation. We can do better. This first term comes from a horizontal line. The second one comes from this tangent. The next thing to be doing would be to try and compute a parabola that's nicely fitting to that curve. And the next component of our approximation would then be the second derivative at this position times hv squared over 2. So if my original curve, capital V, was a parabola, a quadratic parabola, I could add these three terms and the result would be exact. Actually, you see, the way I've drawn it, it's not quite a quadratic parabola, but when we close to x1, when h is small, when we're close to x1, this somehow reddish approximation is pretty good. The Taylor expansion looks like this. The potential at x2, that is the potential at x1 plus step size times initial velocity. That's equal to the potential at initial position plus what we get from the slope of the tangent, the derivative of the potential with respect to position at the initial position times step size times initial velocity plus, and now the term that we get from the parabola, second derivative, a square over 2 plus, and as you go on, you'll find that the next term will have something like h to the third power and so on. The official notation for that is big O of h to the third power. If you want to look that up, this is called Landau big O notation. Now we're going to apply this approximation to our energy calculation. What I'm interested in is the potential at the position after the step minus the potential at the position before the step. So what would that be? The potential after the step minus the potential before the step. See, you subtract v of x1 and we are left with the derivative of the potential times hv1 plus the second derivative times hv1 squared over 2 plus something of order h cubed. The derivative of the potential energy with respect to position has a physical meaning. Let's look into that. Actually turns out that this derivative is nothing but minus the force at that very position. Why is that the case? Let's look at this valley. When we're sitting here in that valley, and we're trying to move a little left or a little right, we should not be experiencing any force. So the force would be 0 here. Same thing on top of this mountain. If you move left and right on the top of that mountain, you should not be experiencing any force. So force is 0 there. When I'm here on the downward slope, I should be experiencing a force to the right. I can roll down the slope. The force should be down the slope. The force should be positive. When I'm here and try to move forward with x uphill, I should be experiencing a force directed against my motion. As I move uphill, the force is negative. And so on and so on. And if you look closely, this pretty much looks like minus the derivative of the potential. So that's the relation between force and potential. The force is minus the spatial derivative of the potential, which means that the second derivative here equals minus the first derivative of the force. Now let's collect what we have. So what was my original objective? I wanted to compute the gain in energy, or potentially also a loss in energy, E2 minus E1, the energy after the step minus the energy before the step. The first component is due to the change in kinetic energy. These were the two terms that we computed. And now we have to include the change in potential energy as well, which is this. Minus the force times h times initial velocity minus the first derivative of the force times time step times velocity squared over 2 plus some remainder. So these were the two terms. This is due to the derivative of the potential, and this is due to the second derivative of the potential. And we've got some remainder. So, nicely enough, this first term and this third term cancel. Then we've got two terms with an h square in them, plus something of order h to the third power. Let me combine these two terms with the h square. That would be the force at the start squared over m minus the derivative of the force at the start times the initial velocity squared. You see, this velocity comes from there. Now I want to get an idea why this is positive, at least on average. Why does energy grow on average? Let's apply some crazy looking algebraic manipulations to the expression in the parentheses. I introduce another copy of that first term to say 2 times the force squared over the mass, but I subtract that one again, so no damage, minus what we had before. So this should still have the same value as this expression, multiplying the first term by 2, but I'm subtracting it again. Let's look at the second term here. It's the force at the initial position over mass times force. Force over mass. We've seen that before. I can compute the force at the initial position divided by the mass by V2 minus V1 over h. So this is v2 minus v1 over h times the force at the initial position. Now for the third term. F prime, the spatial derivative of the force. This ought to be something like, by how much does the force change as I move from x1 to x2, over, by how much does x change? Now great, x2 minus x1. This is an approximation for the spatial derivative times v1 squared, but this is just an approximation. So this is why I put an O of h in here. If I look closely, I get other terms in that. H times something plus h squared times something, and so on. And I also look at the v1 here. Let's go back to the Forward Euler method. I can compute v1 by subtracting step size times force over mass from v2. So that's one way of computing v1. v2 minus step size times initial force over mass. And for the first copy here, it's v1 squared. For the first copy, I'm using the other equation. v1 equals x2 minus x1 over h, which by the way is not an approximation. We're using the definition of x2. This here was an approximation. We're trying to compute the spatial derivative of f, but this here is not an approximation, but just the Forward Euler method. x2 is defined in such a way that this ratio is v1. Exactly. So what can we do? Now you see that x2 minus x1, x2 minus x1 cancel. So all of that expression would become f of x2 minus f of x1 over h times v2. And then we have got something times h and something of order h. All of that combines to something of order h. Let's back up a little. What was the objective? I wanted to compute this expression. Now we see that some parts cancel. There is v2 over h times the initial force with a minus up front, minus initial force times v2 over h. So this one and this one cancel. And what we end up with is the following: 2 times the force squared over m minus, which makes it plus, initial velocity over h times initial force, plus initial velocity over h times initial force, minus, makes a minus, final force over h times final velocity, and something of order h. In case you're wondering, this is plus order h with a minus up front, and I'm still writing plus order of h here. Minus h or plus h, both are of order h. The sign in front here does not matter. So that was the energy difference, actually just this expression in this parentheses. Let me write that down again. The energy difference is h squared over 2 times the expression that we've just manipulated here. So that would be this expression, 2 times the initial force squared over m plus, let me pull out the h, 1 over h, initial velocity, initial force, minus final velocity, final force, plus something of order h times h squared. So let me pull that out as plus order of h to the third power. So this is what I get for the difference in energy. The energy after the step minus the energy before that step. What I'm interested in is not just the single step. I want to look at a finite amount of time being simulated. So I want to do tons of steps. So I need E3 minus E2 and I need E4 minus E3. All these increments, typically increments, not decrements, of energy and so on. And maybe some final one. Let's call that En plus 1 minus En. I want to simulate a given time. So this n should be that fixed given time over the step size. This is how many steps I need. So this difference, E3 minus E2, would be pretty similar to what we've computed, but it would have an x2 in there. It would have an v2, x2 in here, v3, x3 in there. Similarly for E4 minus E3, this would be x3, this would be v3, x3, v4, x4, and so on, and so on. And the final one would have an xn in here. We would have vn, xn, and vn plus 1, xn plus 1 in there. What I'm eventually interested in is the total gain in energy, En plus 1 minus E1. How much energy did I accumulate over these n steps? And the trick is just to add all these differences. If you add all these equations, you get what mathematicians call a telescoping sum. It shrinks to just two terms. You can push it together, so to speak. If you form the sum of all these equations, you get E2 minus E2, these two cancel. E3 minus E3, these two cancel. E4 will be cancelled by something here, and so on and so on. Obviously, En is going to be cancelled by something in the line before. What we end up with is En plus 1 minus E1, what we want to have. Nothing cancels here. We keep on adding. So we've got h squared over 2 times the sum of all these terms, plus, and now there's again a telescoping sum, minus v2 f of x2 plus v2 f of x2. These cancel, these cancel, these cancel, and so on and so on. This is going to be cancelled by something in the line above. So all that's left is 1 over h times initial velocity, initial force, minus final velocity, final force of the very last step, plus a remainder. Now we have to be careful. We include capital N of these remainders, so that would be of the order n times h to the third power, or t over h times h to the third power. Let me clean this up a little. This is h squared times 2 over 2, cancels, times the sum n equals 1 to capital M f of xn, I missed an x here, sorry, over n, plus h squared divided by h, so we've just got h over 2 times this difference. Initial velocity times initial force minus final velocity times final force, plus, let me pull that t out of that O symbol, t times something of the order of h squared. What's the meaning of that first term here? You're summing forces squared over m. That's something like 1 over m times the number of terms we are summing times the average of the square of the force, the temporal average. That's the same. You sum the square of all forces. That's the same as computing the total number of forces times the average. The number of steps is the total time divided by the step size. So the first term becomes h squared over h, is just h, times our total time, capital T, over m, times the temporal average of the square of the force. So what do we get? Where does the growth, the artificial growth, come from? It's that first term. The square of the force is never negative. Typically it's positive. And you multiply by a positive number. This is a positive number. And the contribution of this number is proportional to the step size. If you double the step size, this error will be doubled. In addition, it's proportional to the total time. If you simulate longer and longer periods of time, this error is going to increase. That's the phenomenon we're seeing there's an artificial gain in energy proportional to the step size and proportional to the total time. So here we see growth proportional to the step size and proportional to the total time. The second term is proportional to the step size, but there is nothing proportional to the total time in it. This does not grow as the time goes to infinity. Actually, it does not grow if the velocity always stays bounded and if the force always stays bounded, which should be the case in most systems. So this stays bounded. And then we've got some remainder, which may come into play at some later time, but it's pretty small. It's of the order h squared. So as you shrink the step size to half of its original value, this first term is only half of that value, but this term here will be about 1/4 of its original value. I could say that is negligible. So we've identified the culprit. This is the term that determines the long-term behavior of the energy in the Forward Euler method. Actually, this term also hints at a pretty simple way of adapting the step size. Whenever the square of the force is large, you should be reducing the step size. And one final thing, when we're dealing with symplectic methods, this term obviously has to vanish. We just have terms of this sort.